Hello friends, welcome to my channel. Let's have a look at problem 2334 together again. Subarray with elements greater than varying threshold. And in the current video, I'm going to share a solution using disjoint set union. So in the previous video, we shared a solution based on stack. So the stack is this structure used in that solution. So if you have time, so you're welcome to look at this corresponding solution video. The solution here in this video is partially inspired by the solution for Leetcode 128. So if you have time, it's also a good idea to have a look at the solution for this problem. So with that said, let's look at the analysis directly, so without reading through the statement again here. So let's look at a generic subarray. Let's call it S of nums with length k. So the requirement of this problem is that every element y in this subarray S is such that y is greater than the threshold divided by k. So this statement actually, or this condition, is not straightforward to verify in a programming environment. So this statement is equivalent to say that the minimum elements in S is greater than the threshold over k. So the latter actually is much easier to verify. So with this equivalence realized, so the procedure actually is straightforward. So as the threshold is fixed, the larger the k is, actually the easier the above condition is fulfilled. So the analysis leads to the following procedure. So first, for each element y in nums, we try to find the longest subarray such that it contains this y as the smallest element. In the previous video, so we did this using monotonic stack. So that's actually a standard operation. So here we're going to share a method using disjoint set. So secondly, we want to check if this condition is true. So here in this video, we're going to slightly alter our emphasis. So we want to check for each of the subarray we located if it has achieved the required length lower bound. For example, this condition so is equivalent to say k is greater than threshold over y. So it's corresponding to check if k is greater or equal than threshold integer division by y, then plus 1. So it's okay if we stick to k is larger than threshold and float division by y, because anyway the k is the size of the cluster in disjoint union setting, or the corresponding length of the subarray is an integer. So if after this procedure or the for loop we do not have anything returned, so we're going to return -1. So that's the overall idea. So the part 3 actually is an example walkthrough using the stack method, which we explicitly located the corresponding subarray, and then we check the condition. So we put it here for the consideration that it might be interesting for some of the friends. So here in this video, I'm going to first implement the disjoint set union data structure, and then we will use it to the current problem. So in the implementation, so there are two choices. First, we can implement the disjoint set inside the solution class, or we can implement outside the solution class. So here I'm going to implement the disjoint set union outside the solution class so that it can be used in general. So first, let's do this implementation. So as this comment specified, I'm going to implement a vanilla font. So typically, we can also incorporate path compression, some path compression here, but I don't think it's needed here. And also, in this case, in order to track the size of the corresponding clusters, I'm going to implement a union and a union by font. Right. So here, let's do this implementation first. So the disjoint set union. So let's first look at the initialization. So I'm going to implement two parts, well, self and parents. So going to be a empty dictionary at first, and self sizes or rack. So it's the cluster size. So for in the disjoint union data structure. So here the sizes actually plays the role of racks. So now let's look at the vanilla font method. So this is very straightforward to implement. So here x will be an index. So first I want to check a case is if x not in self parents. So in other words, we haven't add this x into the data structure. Then we're going to do the initialization, right? Self parents x equals x, the self sizes of x equals 1, because it's a single element cluster. It says it's 1. So in the other case, if we have already added the x into the parents or the disjoint set data structure, then we're going to locate its roots or parents. So we're going to return x if x equals its parents, self parents x. Otherwise, we're going to do a self call and then apply to self parents of x. This forms the recursion relation, right? So this is the vanilla font method. So now let's look at the union. So the union I'm going to implement using union by font, union by rank. So x, y are two indices. So first I'll locate the parents or roots of x and y. So here are self font x, self font y. So now the x and y represent the roots of the original x and y state. So then we're going to see if x and y are already in the same cluster or not. If they are already in the same cluster, we do not need to do anything. If they are not, so we're going to check their rack and reset the parents and increment the rack. So let's check self sizes. If the size or the rack of x is larger than that of y, then we're going to set the parents of y to be x. So self parents of y equals x, and then we're going to increment the rack of x by the rack of y. So here I'm forgetting a if. So let's see if. So yeah. So then I'm going to copy this part. So with the modification. So let's check it. So in the case if the rank of x is no less than the rank of y, we're going to set the root of y to be x, and then increment the rack of x by adding the rack of y. So this is very intuitive, because if we merge the two clusters represented by x and y respectively, then the total size is the original size sum, right? So this is the this increment, what this increment does. So otherwise, we're going to do the reverse, right? So we're going to copy this one, and then So we're going to set the parents of x to be y, and then we are going to increment the rank of y by the rank of x. So with that said, I guess that's about it for the data structure or disjoint set. So now let's look at the solution. So the solution is sort of compact. So in between, we will point out the key step. So let's first track the information for the length of norms. So then we're going to locate for each number the corresponding subarray, and then check if the subarray size has achieved the required lower bound, right? So now let's do this. I'm first introduce a variable just for clarity. So required length per number or per index, the same thing. So here basically for I and y in enumerate the norms. So for each y, if y is the minimal element, then the corresponding length actually is nothing but so we need to greater than this number, t divided by y. So because let's try to use interdivision for preciseness. So we're going to use this, right? So t interdivision by y plus 1 is the required length in order to satisfy the condition. So let's sort it. The reason we do this sort is twofold. First, we want to start from the shortest required length. So that's one thing. And the second thing is that it has a relation with the order we add the number to the disjoint set. We want to add the larger y first, because the larger the y, the smaller the required length, right? So that's the role of the sort, twofold. So now let's do this genuine real work. Let's initialize this DSU, so disjoint set union, and then we're going to traverse this guy, required length per num. So for required length and IDX in this guy. Then first I'm going to add this IDX to the data structure DSU, right? So I'm going to because it's find, so which do not. So let's so DSU find IDX. So after we add this one, then notice that when we explain the role of the sort, so the second item is that we first add the larger elements, right? So once in the process, if we check the IDX already in the data structure, it corresponding to numbers larger than the current number we are looking at, or at least no smaller. So let's check if IDX minus 1 in DSU parents, right? So if so, then it means there's already numbers corresponding to this index in the data structure, which is larger than the current number corresponding to IDX. Then we can do the disjoint union set union operation, right? So let's do DSU union IDX minus 1. This actually corresponding to merge the two clusters represented by the parents of IDX and IDX minus 1 respectively. So similarly, we can check this one, DSU parents. Then we do DSU union. So but here we need to change this one to be plus 1. Here we may be wondering, so why we check IDX minus 1 and IDX plus 1. The reason is that the subarray requires contiguous indices. So with that said, actually we have already set the cluster for this IDX. all its parents. So then let's track the length. So the subarray length, so it's actually the cluster size that's containing the IDX, right? So first I'm going to DSU find IDX. So this is the representation of the cluster containing IDX. Then I'm going to track its size, DSU sizes, right? The size is an attribute. So this is the subarray length containing the number corresponding to IDX in nums. So let's check if this subarray length has already achieved the required length. That is this guy, right? If this is the case, we're going to return the subarray length, and we are done. So otherwise, so if after this for loop nothing has returned, we're going to return -1. So this is the full solution code for this problem. So again, this thought is important, and the order of adding the index to the data structure is also important. We first add the larger ones, so that when we do the union operations, we know we merge elements larger than the corresponding elements we're looking at, or the current element we are looking at. So it's a time to do a special case check. Let's see. It passes the special case. Let's do another one. It passes the generic case. So with that said, I would also like you to share a solution that does not pass the generic case check, is time limited. So, but the idea is the same as here. So here I used a like this. After I thought, for each index I want to use sliding window to locate the longest subarray. But this solution is very intuitive, but it's time limited. So let's come back to this solution. So here I would like to ask one question. So for this problem here, Leetcode 128, so the question is, can you solve it using union find? So the union find actually plays a role of partitioning the indices in problem 128. So I guess that's possible, and it's good to have a try. So with that said, I guess that's all about it for this problem. Thank you very much.